Okay. Hi everybody. My name is Michele Focchi. I'm a researcher at the Istituto Italiano di Tecnologia in Genova, and with you I will teach you this course on Introduction of Robotics, together with my assistant Octavio Villarreal, which is also working with me as a postdoc in my institution. First, I would like to give you some information on this course. And as you know, the schedule, the room number now it's 107 because it was changed a week ago. I checked your website with rooms, and our lectures will be only on Monday and Tuesday. Sorry for this as well. So I will update this in the slides. So as a rule, I will continuously update the slides because this is a new course. So if I spot errors and modifications, sorry, it's very hot. I will update the slides. And the course is available online in Moodle. We try to stay within March and May as total number of hours for the course, because also I have other duties because I'm working in another institution, so I had to kind of share the load with my colleague of Octavio, and I will mainly do the first part of the course, the first 40 hours, and he will maybe take care of the last ones. And he will also participate to the lab sessions. So he will be present with me to help you in the lab sessions. As I said, 5 hours per week, and the course is 6 credits. Some of you that are from D have 60 hours of course, while the other ones from DZ, they are only 48. This is kind of an organizational issue. We will see at the end, at the final exam, how to deal with this. If do more questions for the guys that have, let's say, 60 hours, or let some of the material be covered home from the ones that have less hours. The course material is mainly composed of PDFs of the slides and of the lab sessions. There is no textbook, reference textbook, because this is a course which is very, very broad. It covers many topics. And because we have only a limited number of credits, I could not go very deep on each topic. So we'll give you a bird's eye view, a brief introduction, giving you the key pointers for each topic that you can develop further if you want to continue on this direction. But at least you have a broad view. This is what I was requested from Professor Luigi Palopoli, which was the one that was organizing, I think, your curricula. So this is the Moodle code. I noticed today that some of you could not see this in your. Could you access the Moodle?
No, it's fixed.
What?
It's fixed.
It's fixed? Ah, okay. Because
the other day, I think on Sunday or something.
Yeah, because it was not active yet. But some of you told me today that yeah, there are issues in accessing it. So I will check this anyway, because I will upload the material in there, or I will find another way of doing this. If you have any problem in accessing the Moodle, just send me an email and we will sort out how to do. Yeah, As I said, that the slides will be uploaded in this site and will be updated continuously along the course. So if you want to be sure you have a latest slide, just download the latest version of the slide. Because as I said, being a new course, I'm continuously spotting some typos or some inaccuracies. And I think also the recording I will put on the site, such that the ones that are following online and also asynchronously that you want to check the lecture later on can have a look to the class. The course has some prerequisites. In particular, in terms of math, I assume that you have some knowledge on multivariable differential calculus, how to compute a gradient, how to compute a Jacobian, what is a Taylor series expansion, how to differentiate with the chain rule. So not much. In terms of linear algebra, I expect you to have an intuitive grasp on the concepts like eigenvalues, eigenvectors, what is the rank of a matrix, what is a null space. I will recall this, I will refresh this, don't worry, but just to know what is a positive definite matrix. And if you want to refresh this or you don't remember or you want to know more, there is a very nice course of Gilbert Strang that are, it's a book, and are also some lectures that are available online with videos, and it's very nice and very clear. In terms of dynamics, we assume you have some knowledge on Newtonian dynamics in 3D, on the concept of work, kinetic energy, potential energy. So something you should have seen in Physics 1 or stuff like the mechanical physics. Another point is control systems, because robotics is heavily based on the fact that we want to control, after we model the robot, we want to control it. So it's very good if you have some previous knowledge on control systems and automatic control, which means, for example, knowing what is a state space representation, what is a transfer function, and some idea on what is stability. I will anyway try to recall this, but I will assume you have some previous knowledge. Did you do control systems or similar things before, or how many of you have this knowledge? Okay. Anyway, I will do a specific topic recalling all these topics about control before introducing the control for robots. That is a more convoluted one. So in essence, if we want to summarize the goals of this course, we will achieve a basic understanding of what is a robot, how to classify the robots in terms, for example, of kinematics, or what are the functional units of a robot, what are their sensors, their actuators, and how do we interact with this kind of elements, programming them or calibrating them or measuring quantities, and also some signal processing. As you could see from the syllabus, there was like a small topic on signal processing. Then I will provide, the second goal is to get some theoretical tools to analyze the kinematics of a robot and its dynamics, and to plan the motion. So the concept of forward kinematics and inverse kinematics, that allows you to compute the position of a point of the robot given the position of its joints. I will discuss today what is a joint and what are all these words that I'm saying you. If you don't know, don't worry. And then we go from the kinematics, which is the description of the motion, to the dynamics, that is a description of the cause of the motion, so the relationship between a force and an acceleration, in essence. And then once we have the model of the robot in terms of kinematics and dynamics, we can think about design the controller to move this robot. We need a model of the robot because if we have a model of the robot, our controller it's more performant. It's able to provide an action, a control action to the actuators that it's taking into consideration the dynamics of the robot. So it will be more able to create a very fast motion and be more accurate. Then the third goal is the practical implementation of what we saw in the theory. This means we prepared some labs, either in MATLAB, just one, or in Python. And this is for you to, in essence, be able to see whatever was taught in the theory, how is implementable in practice, and have a simulation of this that allows you to draw conclusions, plot variables, and so having like a framework to simulate the robot and see their behavior and design a controller. So in the introduction, after this introduction of today, we will talk about sensors. What are the sensors in robotics? What does it mean measure a sensor, measure a quantity that is provided by a sensor? So all the kind of errors that you can see and how to mitigate them. Then I will discuss about the different kind of sensors in robotics, that proprioceptive sensors, exteroceptive sensors, and some signal processing. The actuation part, so what are all the types of actuators, electrical actuators in the specific. I will talk about electrical actuators because are the mostly used in robotics. Despite in my lab, we use hydraulic actuators. You will see in a few minutes some videos of our robots. Then an important point is whenever you have electrical actuators is to have a transmission, which is a gearbox. So something that amplifies the small torque of the electrical motor to have a high torque at the joint to move the links. So you can use a very small motor rotating very fast and amplify its torque to the joint. And then I will talk about some non-idealities like friction, backlash. When you have some place, when you machine the part and the part is not perfectly machined, then you can have, in the transmission of motion, you can have some loss of actuation. This is very, very bad for the controller. Dead zones, which is what you have whenever you have valves. And then some control basics, as I told you. The number of hours here is just indicative. Since it's the first time I do this course, for me it's very hard to have a proper estimate of the time. And so take these numbers with a grain of salt. And then in the control part, we have the first lab, that is a MATLAB based lab, wherever we will implement some PID control laws, which is the most basic controller you can see, and but is also the most widely used in the industry. We see how to tune this controller, how to design them, And then there is also a lab on Python that will tell you some basics on Python for those of you that don't have a knowledge of it. How many of you do know Python or have heard about it? Okay. Okay. For the others, anyway, this will be enough to do the labs, because the other labs, apart from the first one, they are written in Python code. And this lab will be taught by Octavio. Then we start with kinematics. As I said, forward kinematics, inverse kinematics, dealing with the redundancy. Whenever we have redundancy, whenever we have more degrees of freedom than the ones that we need to perform a task. So think about like an arm, a human arm. Like the task is to keep the end effector, which is the tip of the arm here, and you still have some internal motion. And this is redundancy. And singularities whenever I lose completely motion, for example, in this direction. And when I have the arm completely extended, I cannot move in that direction. Until I'm not in that point, in that configuration, I can move in this direction. Whenever I reach, I lose mobility. So singularity is whenever you lose mobility. Dynamics, I will first talk about statics. So whenever there is no motion. So no relationship between forces, for example, at the joints and at the end effector when there is no motion. And then I will move on to introduce the dynamics and how to compute the dynamic model of the robot. We will see different strategies. And then all this will be done without any contact. So in free motion, the arm will be moving in the space without interaction. Then we will consider the interaction forces. So what happens with the dynamics when the robot gets into contact with the arm. And finally, we will introduce the control for a robot, for a manipulator in specific, extending the idea of the PID controller for one single motor to N motors, so to all the joints of the robots that moves together to achieve a certain motion of the end effector, for example. And all this controller, whenever there are more than one degrees of freedom in the robot, we will have interaction between the different links of the robot. And so we will see inverse dynamics, that is an approach that allows you to compensate for these couplings between the different degrees of freedom of the robot. Then the joint space control topic will have the lab related to that, which is the lab on joint space control, again in Python. And then finally, the last topic will be the task-based control, which is, so joint space control, the control law is written in the joint space, while the task-based control, we close the loop, we write our control law in the end effector space. So in the Cartesian space, I say we want to control position and orientation of the end effector, not the angular position of the joints. And also task-based control has its own peculiarities. One of them is orientation control, which is kind of tricky because it's not like controlling the position. To control the orientation, we need to consider the a representation of the orientation. There are many different representations, and we will see each one of them. And finally, interaction control. So we will use the interaction dynamics that we saw in the dynamics and extend it to create a controller that is able to deal with impact, with the contact forces that are the ones that happen, for example, when a robot interacts with the environment to cut a surface, for example, or to share some load, while in case of a legged robot, for example, that works with a human and wants to bring some weight, and or it's a legged robot, for example, that hits the ground with the legs, it's a force and needs to be able to use this force to move forward. So interaction control, it's more recent. Originally, the robot had no interaction at all with the environment. They were just moving and doing position control, moving stuff. But whenever we got to interaction, the control law become more complex and more tricky. For each lab sections, so we'll provide the code. We will see how to do. We didn't decide yet. Our first attempt is to provide you, let you do some of the exercises alone, and then in the second part of the lab we go through that, providing the solution and discussing the results, because some of you last year told as a feedback to the other professor Andrea Del Prete that was useful for them to see how the things were implemented by the teacher and see them discussed during the lab rather than implementing themselves all the time. So you can still do it, try them at home, but during the lab we try to also to show you the solution of the exercises. There will be, as I say, we'll say later, an optional question that we will not provide, that if you reply properly to that and do a report, the final evaluation will count as 3 bonus points. So on the final score, you will have 3 points. So if you want a laude, you need to do that, because with the final exam, you can get only to 30. So write code, not so much, analyze the results. Together with the Python code, we provide a simulation environment with a viewer that shows you the robot that moves, so you can see what it does, and also the plotting features. And we will discuss, of course, about the result, changing parameters, and see how the thing change according to the parameters. So as I said, there is one lab on control that is a simulation and control of a DC motor, so of an electrical motor, the most simple one. The design of a PID controller and its tuning, and this lab is mainly done in MATLAB. Then there will be the introduction to Python, a lab on kinematics with some exercises on whenever we will discuss in the kinematics lectures. A lab on dynamics, where we'll do exercises to derive some dynamics quantities. The labs on joint space motion control, and the one on fast space motion control. And to the labs, you have different choices. You can use. We need to see that if it's possible, if it's convenient. If everybody of you, it's okay, we can think about, I can provide you, you can bring your own laptop and you can work with that, or we can go to the lab, to the PC, your own, I don't know, if you have you should have a facility with PCs in this building that you can use. So tell me what you prefer. If everybody of you has a laptop and it's willing to work with that, then for me, it's okay. We stay in this room and everybody is doing the lab with his own laptop. And to do that, I provide a virtual machine because the Python labs are on a Ubuntu operating system. So for the ones of you that don't have Linux or don't know how to use Ubuntu or don't want to use that, there's a virtual machine that you can install in whatever computer you have, either a Mac or a Windows machine, that contains everything you need. It contains Ubuntu, the Linux operating system. It contains the libraries that you need for the lab, the simulator, and all the Python code already installed. Otherwise, you can, there is a Docker image, which is like a container, again, with everything set up. But this Docker image, you can use it only in Ubuntu. And you can also decide to do that. The advantage of a Docker image is that you don't have to worry about dependencies, because there are many libraries the code is dependent on. Otherwise, you can do yourself the installation of all the libraries following this instruction. The project is a repository on GitHub that you can download, and there is a README file that tells you how to install all the dependencies to be able to run the Python labs. Do you have any question? Everything is clear. So as I said, evaluation, this year we think we will not do any assignment. There will be only a final exam written with open questions on the course material. And as I said, there are some bonus points that to get them, you need to write a report on the results of the optional lab questions that will be present on each lab. That will assume, of course, that you solve also that you're able to run also that you understood also the other question of the lab, because they're the most difficult ones. And this will count as 3 bonus points and will be valid only if all the labs are delivered. All the questions are delivered from all the labs. Finally, here there are some resources. As I said, there is no really a textbook available, but for linear algebra, there is this book of Gilbert Strang, to refresh it, Introduction to Linear Algebra, with online lectures. And for linear system, we have these other books. The mostly used is Feedback Control of Dynamic System from Franklin, and its digital version. So the version for digital control system and not for continuous control system, again from Franklin. Then there are online lectures, very nice, from Stephen Boyd, which is a professor from Stanford University, and other sources from MIT. In robotics, the Bible of robotics, it's from an Italian professor. I don't know if you heard about it, Bruno Siciliano, and it's from University of Rome, La Sapienza. And this is the most important book for robotics. So I suggest you, if you don't have it, to buy it. And it covers a good percentage of the topics, especially on kinematics and dynamics, and also sensors, not sensors, but more control, let's say. So 50% of the course material it's there. And this is another book, Sistemi di Automazione Industriale, is an Italian one, which is again as a good level of, so it's not going very deep in the topics as we will do in this course. So it's not too detailed and can be helpful. And other 2 resources which are very good are the course online of Alessandro De Luca, which is again from University La Sapienza. And all these lectures are online with the slides, and are very nice. And I was heavily basing my slides on his course. And then there's also the guru of robotics from Stanford University that is called Osama Khatib, and he also provided some online lectures on robotics, on basic robotics, and then a book from Craig, Introduction to Robotics. It's a bit more convoluted and complex. So, as I said briefly before, who am I? I'm Michele Focchi. I do the research on all since 2010 on quadruped robots at Istituto Italiano di Tecnologia, which is a robotic institute with not only robotics, we do neuroscience, we do nanotechnology, but there are almost 400 researchers in robotics working there. And I was involved in designing quadruped robots and working on the control of the quadruped robot that I designed that is called IQ. It's called IQ because it stands for hydraulic quadruped. It's very not really a smart name. It's just whatever it does. It's just an hydraulic in a quadruped, so we call it like that. Then from control, I moved to locomotion and planning what? Planning trajectory to move. So to move, make the robot move on a rough terrain, on let's say on rocks, on moving soft terrains, and you need to plan trajectories for each leg and for each foot and for a central mass to move around. And so at the beginning, during my PhD, I was mainly working on control, and in particular on the control of stability. So how the robot keeps stable while walking. And if you, for example, you push it, it will try to not fall. And some strategies to preserve stability. Then some planning on rough terrain. You see here all these rocks and rubbles. The robot is traversing in an adaptive way this kind of terrain. And you will see that the rocks are moving. We will see a video of that, and everything is unstable. So you need to continuously be able to replan the trajectory to adapt to the terrain, to see that, to avoid that the robot falls. And then as a researcher, I was getting fascinated on soft terrain. So let's say you have a foam here, and the robot needs to be able to walk on the foam without falling. This like okay. Replanning, what I said, that the robot needs to be able to continuously replan trajectory. If you kick it, you will need to notice that there is a push, a lateral push, a disturbance, and replan the trajectory to accommodate and don't fall over. And then also some more involved strategies to consider, for example, the actuation limits of the robot. The robot is not able to actuate any force, has a limitation in the force that it can actuate. So in the planning phase, you need to consider these limits as well. It's important. Otherwise, you plan a trajectory that is not feasible, that the robot cannot realize with his own actuators. Then Octavio Villarreal, my assistant, is, as I said, a postdoc. He works as well with me on quadruped and locomotion, and he likes to work on dynamic locomotion with vision. So using the visual feedback of the robot to create a map, you can see here, and use this map to take decisions. So in the case of a gap, you can, for example, correct the pose to stand up on a pallet, to walk on a pallet, and when there is a gap, you want to adjust the foot location to avoid the gap, to don't put the foot inside the hole. In terms of notation in the course, we'll first, the course, half of it or even more, it's written. So only these initial lectures will be on let's say on a typeset of PowerPoint, but the other part of the course it's written with the tablet. This is just because the lack of time. There was an enormous amount of material, and I had to choose if concentrate on the content or the appearance. You will like it. The drawings will be fancy, a little bit vintage, but don't be surprised if you see a mix of these graphics. So this means advantage and pros. This means the minus means disadvantage, cons. This means definition. When I cite a paper or a scientific publication or a book, I put between square brackets. And when I put an O, it means that is an optional slide that is for just your in-depth study, but is not part of the evaluation. Will be not considering the evaluation exam. And then in terms of math, we have can you see here? You can properly see what is written. Okay. So whenever it's I 3 times 3, it's an identity matrix, which is dimension 3 times 3. Whenever you see something like this, it's a skew-symmetric matrix. I will explain you what is associated to the cross product A cross something. So you will see this along the course. Whenever I talk about frames, I mean both. A frame is composed both of an origin point and of an orientation, so 3 axes. So not only the axis, but also the origin of a frame. This is the coordinate, for example, point P with respect, this is VRT with respect to frame W. And this is the position of point B with respect to A, another point A, all expressed in a frame W. And this is the inertia of body I. So whenever you have a rigid body, you will have a tensor of inertia, so a 3 times 3 matrix. And this can be expressed in a frame. Would be, for example, the link frame, the word frame, and this is how we do. And a wrench, it's for now is like a generic 60 force. So the simplification we consider like the tuple that contains both the linear force in the torque in the moment. So a 6D element of a vector space. Do you have any question for the introduction? Yes.
If I attended the course of the data, can I use virtual machine or I have to download the?
Yeah, it's a bit. I don't know. It's a good question. I haven't tried my code on this one. The dependencies are different because he's using another viewer, for example, and I'm using a ROS-based viewer that is called Arvis. I also use Pinocchio, but I use other things that I'm not sure he has in his virtual machine. What you can do is you can follow the install instruction for Ubuntu 16 and install the dependencies that you miss. If you want, you can just install the dependencies for my code, and if you install of them, my code should be able to work. But I'm not sure because Andrea is using Python 3.5, I think, and I'm using Python 2.7. So I'm not 100% sure it's possible. I should try, and in the next weeks we will test better these labs. So, but you can download it. It's 10 gigabytes or 15 gigabytes. Okay. So we go to the second part. That is the introduction. Okay. So first, let me talk about what is robotics. Let's have a definition. What is robotics? And there's not really a clear definition. Robotics is a branch of technology that deals with design, construction, operation, application of robots. But what is a robot? It's a bit more complex to define. There are multiple definitions online. You can find, I don't know, machine capable of carrying out autonomously some task that is programmable by a computer, or a manipulator, this word, manipulator, that is able to move material parts, tools, again, performing a variety of tasks, or simply, I don't know, a programmable device. So all these definitions are correct. And in essence, they have to do with the fact that there is some automatic way of executing a task. So a robot is able to execute a task, was invented to execute a task in place of a human, or a task that normally a human would be doing it, we let the robot do. There was always a very tight loop between the science fiction and the evolution of robotics technology. In particular, in the past, let's say even ancient Greece, humans were fascinated by the the idea to have automated robots, automated machines. Here you see the myth of Talos, that is a giant that protected the island of Crete. And there's also in the Mary Shelley novel, Frankenstein, they were describing the creation of a sapient creature. And back in the 18th centuries, or even before, were built some machines to perform a predetermined sequence of operation. You see Da Vinci humanoid on the left, and some maquettes that were just executing a task alone. So they were very nicely built, but they were just doing these motions, which was working, but not for any use, just for entertainment. And the word robot came out with the writer Čapek, which is a Czech writer that created his play Rossum Universal Robots, and talk first about the term robota, which means forced labor. So again, replacing humans in doing some work. And then came out the definition of robotics, first with Isaac Asimov, with the 3 laws of robotics that are that, I don't know if you know them, a robot must not injure a human being, or through inaction allow that a human being is being injured. And the second law is that the robot should be able to obey the orders given by humans, except whenever they conflict with the first law. So if another human say, okay, kill this other human, the robot cannot do that. And the third law is that the robot must protect himself as long as it doesn't contradict the first and the second law. And there are many movies from Star Trek, Metropolis, Star Wars along the years. And the problem with this is that people think that robots in the reality should be able to do whatever they see in movies, but this is very far from reality in essence. So we take inspiration from science fiction, but we are still very behind it with respect to what you see in movies. And the first application in the last century of robotics are in the industrial field, and in particular in the welding task. Everybody knows what welding is. Okay, especially in the automotive field, wherever there was the mass production of cars, welding was very important in the assembly lines to put together the parts. And one requirement for welding, very important, is that the robots, the position of the welding tip should be very precise. Otherwise, the welding is cutting or breaking. And exactly, robots are very good at positioning and accuracy, doing a very accurate motion. And the other requirements are speed. So robots are both fast and accurate. These are their main capability that was exploited in the industry. And you see on the left, the first mass product robot that was used in the assembly line from General Motors in 1969, or to move material pick and place, so move an object from here to there. And at that time, there were no interaction forces, as we say, because they are tricky. And so robot manipulators were becoming the standard in assembly lines of cars. You see here the working assembly line, where there are many stations around, many manipulators. These are called anthropomorphic manipulators because they assemble the arm of a human, and all the parts of the car are put together and welded, and screws are put in place. And from the chassis to the motor, the car is completely assembled in an automatic way. And this enabled to increase the productivity a lot along the years, and also the precision and the reliability. Thanks to the precision of the robot, you know that the task will be performed repeatedly, always in the same way. And this is the advantage of robotics, because humans are not good at repetitive tasks. They get bored, they get tired, they have intelligence to be creative, not to just repeat the same thing and be precise. But later on, many researchers start to think about new ideas, new application of robotics. And this was Mark Reibert, that was the founder of Boston Dynamics. That is a company, I don't know, I'm sure you saw the robot of this company, like Big Dog and Spot. They're incredible working machine. And recently more in space exploration. So starting from the 70s, in the space rover, we start to see manipulators mounted on top of the. This is in the 80s, so almost 30 years ago, the first legged robot from Mark Reibert in MIT lab, Massachusetts Institute of Technology. And these machines were quite simple in terms of actuation. They were using very simple heuristics. Don't know, for example, open a valve and with a certain timing according to the angle of the leg, and keep it open for a while. So it was some pneumatic actuation in this kind of motions, but they were able to do in somersault. So this is something we are starting to do now these days as a research to realize these somersaults, and they were able to do them with these heuristics, this very simple laws. Here there is a quadruped based on the same topics. And you see here that there are some springs. In this case, these are air springs, so they're air compressed. That it's very important for legged robots to dump to the contact force. So in legged machines, you need some compliance, some non-stiffness to be able to avoid impacts, big impacts that could destroy the robot. And okay, I'm not sure if you can see, maybe. So on the left, more recently, you can see dancing robots from Boston Dynamics. Here on the top right, we see our colleague from Zurich, ETH, and that did a spin-off on quadruped robots, creating the animal quadruped robot. And there are recently more from China, a company called Unitree. That's also made quadruped robots. And this is Cassie from Agility Robotics in Oregon, US, that create this biped. So there are more recently a renewed interest in quadrupeds and in legged robots. And not only legged robots, but also, I'm sure you know recently, the landing on Mars of Perseverance. And exactly in this kind of application, manipulators can be used, for example, to collect samples, to see the presence, search for the presence of water or even life, and in the future to build infrastructures. So build buildings where the humans can go whenever they will land on Mars, for example. So is to prepare the terrain for the colonization of Mars, for example. This is a, and recently we, for example, with my group, we won a project with the European Space Agency to build an hexapod robot that is able to explore the craters that are on the moon or on Mars. So it's able to walk. So if this is a taxonomy of the robots in terms of two axes. In the y-axis, we see continuum from industrial to service. So what is a service robot? Is whatever is not industrial. So a robot that performs some useful task for humans and is able to doing this repetitive task, but is not related to an industrial application. While on the x-axis, we have moving from a fixed base manipulator, for example. This is a typical robot that is you saw before with a very stable and heavy base that doesn't move, and toward a situation where the base is smaller and it becomes mobile. So the robot can move around. So a legged robot, as you see here, is a robot that doesn't have a fixed base, but has a floating base. So it's a base that is able to move around, and the legs are kind of for manipulators connected to this floating base. Then you have surgical robots. Surgical robots, for example, are very important whenever the surgeon wants to be create, for example, a cut on a pharynge, and so is drawing like the cut on a tablet, and the robot with a laser will perform the cut very precisely. So because the robot it's precise and in repetitive tasks, it will be able to do it perfectly. The other thing is that there are some robots that help detect, for example, the loss of attention of the surgeon, that whenever it gets tired, they stop the cutter, they stop the bisturi, or they help him in being precise. Then prosthetics are like artificial hands. At IIT, for example, we have these hands that are commanded by neurological commands from the amputee, so that the hands are mounted on an amputee person that lost his hand, and we are able to command, giving commands from the brain, like opening and closing the hand at least. Then exoskeletons are again, it's a robot that you can wear. So the human wears this exoskeleton robot, and the exoskeleton has two functions. One, in case of a paraplegic, a person that lost the use of his legs, make him able to walk and to move around. And the other one is in case of workers that needs to, for example, carry very heavy loads. They do power augmentation, so they increase the strength of the person in lifting loads. So they reduce the work accident due to back pains and stuff like that. Then we have underwater robotics that could be used to explore the seabed under the and monitoring the oceans. Very important topic nowadays, wherever we have problem of pollution. Self-driving cars and the drones. The drones are can be used for inspection, are mainly used for inspection because they cannot bring very heavy loads, because they can bring a camera, let's say, and they have limited batteries. So the main problem of drones are batteries. But if you think about, for example, inspection of a bridge, that now, if you heard about Genova, the bridge collapsed, and there was a need to inspect. So what is the status of the bridge, of the concrete, because a bridge doesn't last forever. So usage of drone could be in this direction. And also more recently, we have quadruped with wheels. So we combine a quadruped with the legs and the wheels. And whenever it's on flat terrains, we'll use the wheels, moving very fast, covering a lot of terrain very fast. And then whenever it reaches an obstacle like a stair or a gap or some rocks to cross, then you use the legs. So the advantage of legs is that they can traverse any terrain, not any, but with respect to legs, they don't get stuck in a terrain that is, for example, made for humans with stairs and stuff like that. So we will discuss all these robots rely on the concept that we'll describe in this course. In this course, we will focus mainly on robot manipulators, so a fixed base robot used for industrial application. But these tools you can extend, you can easily apply to other domains. I forgot to tell you about human-robot collaboration. Here you will see afterward a slide. Whenever we move out from the industry or in the new type of industry, more futuristic, let's say, we will consider more and more the interaction between the robot and the human in doing a work. And I will tell you how. For example, one way is shared autonomy and bimanual manipulation. In this case, this guy is using two gloves, and with them it provides commands to the two arms. So from a different location, even not seeing the robot, it could, for example, make the robot perform an operation like picking a box or lifting a weight, and using this approach. And sometimes it gets also force feedback from the force that the robot detects at the contact. It's reflected into this haptic device. And this is almost the same topic with a robot called I think this is Justin or from DLR Robotics in Germany. And this is we use this technology, for example, in a project to collect samples. So from another room, we were commanding the robot that was our quadruped with mounted an arm on top, and it was collecting the samples from objects and putting in a bag, and then work again, opening doors. So you can do very complex tasks without programming them. You just replace. And another thing is, it's as I said, the human-robot collaboration. So the worker work with the robots, and the robots provides him the pieces that he needs. For example, in the assembly line, it provides you the tool that you need. You ask for the driller, you ask for this specific component, and the robot will go back and take it and bring you there. So the human can concentrate on the tasks that are more suitable for him, that involves more intelligence, more creativity. And this, to do so, we cannot do, we need to introduce two important topics that are safety and compliance. So the robot should not be completely rigid, because if it gets into contact with the robot, it should be able to, with the human, it should be able to comply, it should be able to be soft and give away from his predefined trajectory. And safety, because in case of contact, it should not harm the human. The other collaborative task, for example, is in this application that was done in our lab. There is like a sewing process where the human at first teaches the robot how to do the motion, and then the robot learns by this demonstration the motion and replies it alone. So again, in legged robots, the state of the art is to implement reflexes. Here the robot is walking on ice, it's almost falling, but recovers balance with prompt actions. These actions are reflexes, are motions that are very fast, that are useful to recover balance. And how these actions are designed by simulation. So we implement our code in simulation. We don't test on the robot. We first try in simulation, and then we test on the robot. So in the pyramid that you saw before, it was like our simulator that is called Gazebo, where we were trying our trotting. And then once everything works in simulation, we try in the real machine. This way, we are sure that we don't do big errors, because we can break the robot if we do the test directly on the robot. So the simulation is very important. And in this case, you will see that whatever I was telling you before, that the robot was traversing is moving on the pyramid, and here is traversing like a terrain with rocks, the big rocks. You see, you can put on the foot on the brick. The brick rolls away, and the robot loses balance, but recovers because of the continuous replanning strategy. Here it's some motions that are some researcher of MIT on a cheetah robot. It's called this one, and they are based on optimization. So the controller is solving an optimization problem that does the optimal thing. And what is this optimal thing? Is, for example, don't apply forces that are out of the friction cone. So in these experiments we did back in 2014 with Andrea Del Prete, and was published more recently, the robot has to continuously press against the walls in a way that was not slipping. And to do so, the force has to be optimized to always be perpendicular to the wall. Otherwise, the robot will collapse, because the robot here is IQ as point fit. You see, as not big fit, so very low friction. And this is done by optimization of contact forces. And machine learning is a new trend, very common in robotics, which means using neural networks, for example, to learn some behaviors. So you don't have to code the behaviors. You simulate, you make many simulation, and you provide a reward. You will see a course with Andrea Del Prete next year on reinforcement learning. And this neural network learns with the rewards that you give. You say, okay, you did bad, wrong reward. Then you did something better to what I want. I want you to stand up, for example. And then all this is coded in a neural network, and you improve this neural network capability with many simulations, and then you don't have, it's very fast, because a neural network is just a matrix multiplication, and you can compute it super fast. So you don't waste time. You don't need to solve an optimization problem. And on the right, we see IQ. It was like crossing these gaps, and was seeing the map of the terrain, and the neural network was changing the foothold location to avoid the gap. So continuously evaluating the map and adapting the foothold location to avoid the hole. And this is like an application of legged robots for nuclear decommissioning, for example. So we say that we want these robots to replace humans, where also in situation where the human could die, think like a radioactive environment or an old Chernobyl situation, wherever you have an old plant with still some radiation to go on, and the robot needs to go there, do a map of the environment, and there are some holes, needs to walk belly down to get through the holes and be able to perform some operation against with some arms. If you mount some arms on the robot, is becoming a centaur. It can do manipulation, collect samples, remove radioactive material. And finally, some people work on soft robots. So we will only deal with rigid robots, rigid bodies, but soft robots are introduced because they are compliant, but they have nonlinear dynamics, are more difficult to model, more difficult to control, and of course more difficult to be accurate, because you cannot control really nicely position. But you can see here a gripper. This is a way to grasp, I don't know, fruit in the agricultural applications. You grasp object, and with this compliant gripper. Finally, one topic is very important. It's simultaneous localization and mapping. So whenever a robot enters a new building, it needs to be able to create a map of the building and know whatever is inside this map. So localize himself inside the map. And this is very important for the robot to be autonomous, because we get many requests from companies that they say, I would like to have a robot to inspect my oil gas plant, my platform oversee with the oil and gas platform. I want the robot to patrol, do inspection, such that I don't have to send humans, because nowadays the oil and gas platform along the sea, they require a person to go there 2 weeks. Then this guy needs to take 2 weeks of holidays, otherwise it gets crazy. And every 2 weeks, and need to replace another person and stays there alone, and it's very risky because it can have an explosion, can have a leak, it can get very it's very hazardous environment. So having a robot walking around, climbing stairs, checking whatever is going on, it's very an interesting things application for. And this is like visual servoing, which is using like
the camera to follow, to track an image, a target. So the target of the controller is here is to detect the image and track the image. So closing the loop on the visual feedback. Okay. I think we stop here for the break. And if you have any question, I don't know how many minutes to do the break, 10, 15, are you tired?
Depends on the.
Okay, let's see what time is now. Okay, let's do 15 and then we continue the last part. Yeah. Also, the others have problems too. Okay. So let's talk now about the what are the functional units of a robot. Brief overview on this lecture. We'll see what are the functional units of a robot. How do we classify robots in terms of their kinematics and workspace, and an overview of the main topics in robotics. So first, you need to consider the robot as a system, and robotics, it's interdisciplinary field of engineering that it's in the middle between mechanics, control theory, electronics, and computer science. So to do robotics, you need to know a bit of all of this and be able to be like the director, like a cinema director that is able to talk with different experts in these fields, let's say technicians that are mostly expert in mechanics or in electronics, and you need to be able to provide the specifications that you need from, for example, an electronic board that needs to provide some capabilities from the code in the case of computer scientists, and some stiffness and strength of the structure, and if you talk with a mechanical technician. And in input to the robot, we have desired commands, or in industry, sometimes they are provided as like a list of high-level commands, like basic commands, like go to here for 5 seconds, then move to another point, stay there other 10 seconds, draw a circular line on this piece. Or, as in the case of, for example, you have an interface, a graphical user interface or a joystick, you can provide commands, high-level commands with a joypad, for example. We do this with our robot, with our quadruped robot. We have a joypad. We just give high-level commands: go forward, go left, backwards, rotate in place, and that's it. And the robot needs to autonomously work out what to do, and so receive the commands from the user and perform some action on the environment. So if it is in contact with the environment, it needs to know what to do. For example, if it needs to pick up an egg or a very delicate object, it should be able to not apply too much force. And to do so, we have several ingredients. One of them are the sensors that detect the state of the robot and of the environment, and the actuation unit that are like the muscles of the robot. So the way the robot perform actions based on the perception that are the sensors. The mechanical units that are the joints, the kind of elements, the actuator unit act upon. And then finally, there is a supervision unit that is the brain. So whatever is the computer on board on the robot or the central unit that commands the robot and tells the robot to the actuators, gives the command to the actuators in order to perform a certain task. So sensor units are divided in proprioceptive and exteroceptive. Can you give me an example of a proprioceptive sensor? Do you have any idea? What? Encoders, very good. Yeah. That's it. Let's say, that's it. Let's see. There is also gyroscopes, because accelerometers, they measure accelerations, linear and angular, but they don't measure angular velocity. So, so proprioceptive sensors are related to the internal state of the robot. I don't know which Lassen pointer is. Okay. And for example, the position of the joints, so the velocity of the joints, acceleration of the base in the case of a mobile robot, orientation of the base. In case of a drone, we have only acceleration and gyroscope because the drone has no joints. It's just 4 propellers, which are creating these lifting forces. And the other class of sensors are the exteroceptive sensors, and these measure the interaction with the world around. And in terms of interaction with the world, it means like interaction forces, contact forces, or vision, let's say, well, visual feedback, map of the environment that the robot it's immersed, and proximity sensors. For example, whenever we have an assembly line and the object moves and the object presence needs to be detected whenever it's passing, and haptic devices. Then we have actuator units that are exactly the, for example, the motors that drives the joints, electric, hydraulic, pneumatic, transmission gears. To amplify, we will see the performance of in terms of torque, of force of the actuators, and the controllers. So each actuator unit should have a controller that controls its position, force, velocity, whatever we decide we want to control. And this kind of control is called low-level control. And it's low level to be distinguished from the high-level control that is a control, for example, that we have on legged robots to keep stability, and while the low level is more controlling the position, the velocity, and the force. Then we have the mechanical units that are the joints of this kinematic chain that represents a robot, the effector, and the links. So the rigid structure of the robot that compose the mechanical units are the links. And these links we consider like rigid body, so not flexible. For this course, we don't assume any flexibility. And then you have a supervision units that it's the high-level control. For example, as I said, controlling the stability, controlling the some high-level task, like if you have a mobile robot that needs to move around in a labyrinth and get an exit, then the high-level controller takes care of controlling the not the wheel velocity, but the full robot position and orientation. And then planning is the trajectory that needs to be tracked by the controller. So provide a trajectory to follow. Also in the supervisory unit, there is this concept of at a even higher level of artificial intelligence and cognition that tells you, for example, in the exploration of a labyrinth, which paths you should go or explore according to a certain strategy, or for example, whenever you have a very complex terrain, you want to avoid the places where there is sand, or there is slippery terrain or rolling rocks, and go on a more, takes decision to go on a more robust, consolidated ground that is less prone to failure. So how does the robot solve its task? First, it needs a control objective, and then a feedback control law. So we need to translate our task into a control objective. If I want to put the tip of my robot from this point to there, I need to find a trajectory that is feasible to reach from the actual point to that point. And this trajectory could be a straight line, or if there is an obstacle, it could be like something like that. So depending on environment, depending on the target, we need to define this trajectory, which is the plan, and with a feedback control law, we track this plan. So we try to give commands to the actuators that are able to move the effector tip from the actual position to the target location, for example. Then once we define this control law, we need to implement it. And usually we implement it by software. So either you code in C++, in a computer, or in a microcontroller. You could even code in assembly if you want. And these are called embedded coding because microcontroller are very small and could be embedded on the joints. So they don't need to be in a separate location. They can move with the link itself. Sorry, with the link. So the autonomy and interaction with the environment is achieved by a combination of perception from the environment and performing some actions. And the actions are determined by the control law and are performed by the actuators that, as I said, are the muscles of the robot, while the electronics part, it's like the nervous system, and the brain is the computer. The computer is the brain. And the perception, as I said, on the environment is obtained through the sensors. The mechanical structure is a sequence of rigid bodies that are called links that are connected via joints. And these joints form a kinematic chain. And these joints can be either prismatic if they have linear motion, they are low linear motion, or revolute joints if they allow rotational motion between links. We need to say that one joint allows only a motion between two links, so either linear or rotational, unless it's a spherical joint, but this is a specific joint class of joint we don't talk about. At one end of the kinematic chain, we have as I said, the base, which is fixed in case of industrial robot, moving in case of legged robot or drones. Usually fixed to the floor in case of industrial robots. And at the other end, we have the end effector. That is the location where you normally mount the gripper, or the part that you use to perform some operation like machining, stuff like that. Then the degrees of freedoms are the degrees of mobility of this robot. And they are normally distributed in the mechanical structure in a sufficient way to perform a task. So in your opinion, how many degrees of freedom a robot needs to position the end effector in the space, in the Cartesian space? Just the position. 3. Position and the orientation only? 3. And both position and orientation, 6 at least. Okay. So why do we would like to have 7 degrees of freedom robots? Why most of the industrial robots are 7 degrees of freedom and not 6? Because of dexterity. So if I have only 6 degrees of freedom, I can approach the task that I want in only one way. There is only one joint configuration of the 6 degrees of freedom to achieve the 6 degrees of freedom task, which is position orientation. But if I have 7 degrees of freedom, I can do, as I said, many ways. I think about this, just positioning this, and I can choose a more convenient configuration, for example, to apply the force. That is, configuration is more useful, more convenient to generate a force. So this is why the redundancy is used to improve the dexterity and the mobility of the robot. The joints, as I said, allow only 1 degree of freedom between 2 links. Each joint allows only 1 degree of freedom. And the joint variable is the coordinate associated to such degrees of freedom. And the way we represent the joints in our diagram are this one for rotational joints, and this for prismatic joints. So in here, you see this is the joint axis of the revolute joints, revolute or rotational synonymous, while this is the linear axis of a prismatic joint. So this joint rotates about this axis, and this one moves along this axis. Then, as I said, we have the base frame at the beginning. This is the kinematic tree of the robot. You have a first revolute joint, then 90-degree axis. We move the axis 90 degrees, and we have another revolute joint. Then we have a prismatic joint that moves along this direction. And then finally, we have another revolute joint. And here you have the end effector, which is now it's represented here. So, or tool frame, while at the beginning of the kinematic chain, you have the base frame. And normally the base frame is attached to the first link of the robot. While usually the end effector frame is located at the central point of the gripper. And this is an example of end effector is whatever really the mechanical part that effectively performs the task that you want to do. If you want to grasp something, you have something like this. If you want to drill something, you will have a driller attached to that. If you want to deburr, you will have a rotating part that we remove the excess of material from the piece you're machining. And actually, because of this, you can replace this according to the application. If your committer, your employee tells you, I want a robot that cleans surface or paints a surface. If you have you want to paint, you will attach how do you call it, a spray. Otherwise, you will attach another element. And as I said, in case of you are handling my objects or grasping object, use a gripper. Otherwise, use the specific tool. The payload is concept is how much load the robot can transport in a precise way, depending on the configuration. So if my robotic arm is completely extended, you think the payload that is increasing or decreasing? Increasing. Who's saying increasing? And decreasing? The payload has the maximum capacity. So it really depends on the strength of the more proximal joints. So if the arm is completely extended and attached force here, the torque will be very high here. And I will reach the limit soon of this actuator. So if you're here, I can bring very high weight, say, depends on the configuration again. But in general, if the robot is completely extended, the use payload capacity reduces. So you can, according to the extension, you can see that now let's forget about the y-axis, but you see that the number of the maximum payload reduces. And for hydraulic robots, the payload that they can sustain is very high. That's why hydraulics is interesting in robotics, because of the capability of have very high power to weight ratio. So in their small actuator, they're able to be very powerful and develop a very high torque and a very high velocity at the same time. While we see with electrical motors, you need to have a trade-off. Either you have high torque and low velocity, or high velocity and low torque. The kinematic structures can be of two types. We have a closed kinematic chain. As you see in this drawing, these are called parallel manipulators, and they are used for pick and place machines. So it's very fast motions, and they have advantage of being very stiff. Or in the flight simulators. You see have you ever been in this entertainment parks, wherever there's a flight simulator where you enter, you feel acceleration, like the robot, the airplane is lifting off, taking off. These are done with this Stewart platform, and that is a disc with the I don't remember how many. I don't remember how many actuators, but it's powered with this kinematic configuration. Otherwise, we talk about open kinematic chain, where the sequence of links, it's open at the end. And this is the case we will talk about in this course. So an industrial manipulator is an open kinematic chain, and a serial, it's called also serial kinematic chain. Then there's a classification about the kind of joints that we introduced. We see here the Cartesian or gantry. This is used in warehouse to move around stuff and pick and place. I don't know, think to Amazon that needs to collect objects. Cylindric, which is rotate. So these are all three are prismatic. While cylindric, it's like a rotational one and two prismatic joints afterwards. Then you have a SCARA robot, which is a two rotational joint with parallel axis, and the third one is like prismatic one that goes down and up, and polar spherical robot, which is true rotational joint or revolute joint, and prismatic at the end. And finally, the articulated robot or anthropomorphic robot that has all revolute joints. So if we talk about workspace, the workspace is the portion of the environment that the robot can have access to. So this really depends on two facts. One is the kind of joint that the robot has, kind of type of joint, revolute or prismatic or combination of both, and the presence of kinematic limits. So each joint, as you see, I cannot move my arm more than this joint more than this. I cannot go beyond because there is a limit, kinematic limit. And the upper one for this joint, it's this. So I have a range of motion that the joint is able to do. And after that, I have end stops. So you could think about also a link that is moving endlessly with a motor. But even there, if you have some sensors at the end, you have some wire that winds up and then you cannot move. In our new quadruped robot, we can do 3 turns and then the wire gets squeezed. So all of them in general have kinematic limits. And so the shape is a workspace. And if you have a Cartesian robot, you see that the workspace is a parallelepipedum. And the accuracy along this workspace is constant. That's why gantry are very good also for whatever you have inside a 3D printer. You have a gantry, you have a Cartesian that moves the tip in 2D, no, in 3D actually, and you exactly have that. And they have good stiffness. SCARA robot is where all the axes are parallel, 2 rotational, 2 revolute and 1 prismatic. The workspace is cylindrical, and the accuracy decreases with the stroke. So if the robot is extended, you have less stiffness and you less accuracy. You're less accurate, while here you are more accurate. Say closer to the vertical axis here, and the stiffness it's high for vertical loads. So along this direction, the robot is very able to very stiff. But if you think about pushing in this direction, is because of the structure is not so stiff. Then this is a cylindrical manipulator, and the workspace is cylindrical. The spherical manipulator was called also Stanford arm and has a spherical workspace. Of course, it's a section of a sphere because of the kinematic limits. So the cut you see here are due to the fact that you cannot move the joints 360 degrees. And the accuracy, as in the case of a SCARA, decreases with the stroke. So as you extend because of the lower stiffness. Then we have the anthropomorphic manipulator that has this workspace. In general, a 3 degrees of freedom anthropomorphic manipulator is equipped with a spherical wrist. So it's another part of the robot that has whatever we call the spherical joint. So free joint, revolute joint with intersecting axis that is able to orient the tool, the end effector. So we are able to achieve any orientation. So with the 3 degrees of freedom, first 3 degrees of freedom, we achieve the orientation, the positioning of the end effector, and then with the additional 3 ones of the wrist, we achieve the orientation. And 60% of the installed robot manipulators have an anthropomorphic structure, and the workspace is it's a large portion of the sphere. The accuracy, it varies within the workspace, as I said, according to the configuration. according to the stiffness. It is different in different places. And here you can see some pictures of example of anthropomorphic manipulators, industrial robots. These are ABB, FANUC. Hook arm it's the lightest. Let's say it has a very small base, and it's one of the most performant in terms of accuracy and quality. So also cost. Then, as I introduced before, the redundancy is whenever you have more degrees of freedom than the task variables. And the redundant manipulators are used, for example, to solve a constrained task, like reaching a desired position in avoiding an obstacle. So you see, you have many different ways to achieve this position and orientation. And if you have an obstacle here, you can avoid it, playing around with the additional degrees of freedom. Here you have only one solution. You have no redundancy for this position and orientation. Here you have multiple solutions, and you can either use to avoid this obstacle or to improve dexterity, mobility in the manipulator. Then what the main robotics topics are mainly for control, perception, estimation, and planning. So we get from the sensor input, and in a very short time, because the robot control needs to be reactive in a millisecond, in 100 milliseconds, or a few milliseconds, depending. If you're controlling force of position, for example, in case you're controlling force, you need to be very fast. And provide what? Provide, according to what you read from the sensor, provide a command for the actuators. And so the estimation is what is the state of the robot, what are the state of the environment, what is the state of the environment, sorry. Estimation is whenever we have some variables that cannot be sensed by the sensors. So it needs to be inferred, estimated from other variables. We will see, for example, that the accelerometers can provide acceleration on the robot, on a legged robot, but cannot provide the linear position. So the linear position of the base of a mobile robot needs to be estimated from, for example, encoder measurements or other elements. We will see in the sensor lecture how. Then we have a perception of the environment and the control and the planning. So while we move toward the planning, in essence, the requirement in terms of frequency of computation is less stringent. The planning can happen, that is, I don't know, decide to go there, move the direction can happen every once in a while the low-level control that tells the actuator drive this current needs to be very, very frequent. And for example, every 1 or 10 milliseconds. Yeah, so as I said, not the estimations whenever you cannot estimate all the states from directly from the sensors. And there is a whole branch of engineering that studies state estimation and deals with the problem of providing estimates for these internal states that are not observable directly from the sensors. And for example, observers are a class of this estimation algorithm. And it's very important because if you want to close the loop on these internal states, we need to know an estimate of them. The perception exactly is the ability to perceive, understand, and reason about the surrounding environment, and use this information for example, from visual sensors. The perception can be divided according to the kind of sensor in proprioceptive and exteroceptive sensors. In the case of heteroceptive sensor, we will see we have vision sensors like cameras or laser sensors, infrared sensors. And a challenge that I showed you before is the simultaneous localization and mapping, which is a SLAM problem that is understanding where you are in the map that you just acquired, and how to build up a map and localize yourself inside this map in real time. So while the robot is moving, for example, inside this. And you hear, for example, a video of a drone that needs to do simultaneous location and mapping, and is building the map in real time, and it needs to be able to, according to this understanding, is to be able to move and steer to enter inside these holes. This is a competition that is done worldwide. Control instead is execute a desired motion, change, for example, joint position, and whatever is able to execute to dictate what to do is the controller. That is in general a mathematical law that based on the concept of feedback drives the system to a desired set of states. So I want to move from here to there. I need to tell the actuator what to do. And the main goals of the controller, one is ensure that the robot is stable, so it doesn't start to shake because of the feedback. Because whenever you introduce a feedback, you can have problem of instability. We will see this in the controller class, the control class. And whenever you have instability, you have the state variables that start to diverge exponentially, and you basically see the robot arm that just drifts away, and it's very dangerous, and you don't want that in any case. So the first goal of a controller is to ensure asymptotic stability. Asymptotic, we'll see, means that the tracking error goes to 0. Reference tracking, so we want to, the controller needs to be able to track the planned trajectory, so follow a desired trajectory, and is doing this by computing deviation between the desired trajectory and the actual position, for example, the end effector or whatever output of the system we are considering. If we want to control force, then the actual output is the actual force. At the end effector, if we want to control position, the measured output is the actual position. And needs to be able to do that with a specified accuracy. So you that are the designer of the controller decide, I don't know, to perform this task, I want to be able to reach the target with a 0.5 centimeter error. It's okay for that. Then you write this specification and you design the controller to have a 0.5 maximum position error accuracy. Or if you do a motion, want to be able to track a motion, a sinusoidal motion very fast, then what is the maximum tracking error that you accept? You decide, I want maximum having a tracking error of 1 centimeter when tracking a 1 Hertz sinusoidal trajectory. And then you design a controller able to achieve that. Of course, there is a price to pay if you are too greedy and you say, I want a 0.5, 0.1 millimeter, and I want to go at 10 Hertz with an electrical motor. Is not feasible mostly because of the actuation. You require so big actuation torques that you saturate your actuators. So the control action, the most accurate and fast you are the higher the control action in general you can have in some moments of the motion. The third point is that robustness. So a controller needs to be able to remain stable even if you have uncertainties. You design your controller based on your model of the robot that we will derive, but your model is wrong. The mass of your robot you think is 80 kilograms, and now it's 85 or 90. It's 10% out, let's say. Then your controller needs to be able to deal with that, cope with uncertainty, sensor noise, because your sensors are not perfect. And also, as we see, coupling between links. This we will see in the inverse dynamics lecture. So here you see, like, for example, a task with high accuracy, but then whenever there is interaction, for example, with the human, the controller is able to give away from the trajectory. This is exactly what we want to achieve in human-robot interaction. So accurate positioning when there is no interaction, and compliance whenever there is interaction. Finally, the planning problem is it's a problem of finding a sequence valid actions to execute a task. So if, for example, the task is to drill a hole there, this point and I'm here, the robot is here, and needs to first create a task, plan a task with a trajectory to move to the location where I want to do the drill, and then perform a motion slower, at slower speed in the direction of drilling, in the drilling direction to create a hole. And then a third task is to exit and move in another place to another operation, for example. So depending on the task, we can have, for example, in case of material handling, you need to just do a point-to-point motion. So from you have grasped the object, you want to move it here, so you just move there. You don't have really to define a trajectory. But in case of machining, where you need to drill a hole or follow a first surface and to remove excess of material, then you need to define every instant reference point to track. This planning could be done either at the joint level or at the end effector level. So we can define the same motion, defining a reference trajectory for the joints or for the end effector. And another way is to, as I said, using graphical user interface or joysticks to drive commands, or we can have reactive motion planning. This is the case whenever you, for example, you have whatever you saw, the robot is sleeping and needs to take a reaction. So we need to modify its trajectory in order to recover stability or to react to the environment in a proper way. And for example, in this situation, the robot is willing to take this cap, but then the box is moved. So he needs to detect that the box is moved towards him and modify the trajectory, the original trajectory he wants it to do, in order to avoid the obstacle, the collision with the obstacle. And to be able to design a proper controller or even design feasible trajectory, we need to have a mathematical description of the robot behavior. So we need a model. A model is a mathematical description of the robot that is based on the laws that govern the motion of the mechanical structure. So a mechanical structure is a set of rigid bodies, and we will see in the dynamics, we describe the dynamics of a rigid body we put all of them together in a chain, and we are able to describe a dynamic model of the robot that tells you how the robot will move given a set of joint torque, actuation torques, or forces. And whatever we saw before, the previous topics, the state estimation, the controller, the planner, they require models. Even the perception that requires models, because, for example, a sensor model can be used to model the non-ideality of the sensor. We can show, for example, in simulation that our camera is not able to see out of the field of view of the camera. We can see that it's not able to acquire samples, a point cloud of the environment fast enough. We can see, add some Gaussian noise on the that represent reality on the sensor acquisition. And these are models of the sensors. And of course, this model can be used in control laws to predict the behavior of the robot and given on this prediction, apply a control action that is more intelligent and will achieve a better performance, because knowing how the robot will move, I will apply a profile of torque that takes into account this, and I will just correct for the inaccuracies between with a feedback law between whatever really does the robot and whatever I want to do for him to do. So model is very important nowadays. The very most diffused format to encode a robot is called URDF, and is a domain-specific file based on XML tags that contains all the relevant information and is widely accepted by the robotics community. Nowadays, everybody uses that, and I really suggest you to do so, and don't write your own model format, because and nobody will use that. And you can share code easily. You can, for example, find online this URDF model for each robot. So you want to test your UR5 robot. This year we cannot work with them, but you have some manipulators in the lab, and we didn't have time to prepare labs with the real robot. Maybe next year we will do that. And for the UR5 robot, you have the URDF model, and you can use that to simulate the behavior of the robot. So in the lab session, you will have the URDF model of the UR5 robot, and you will simulate the UR5 robot. And if you are interested to do a project on that, you can ask Luigi Palopoli to work with the real robot that you have here. So the URDF contains the body layout, kinematic and collision surfaces, the visual appearance, the 3D CAD, the appearance of the links. So you can get from the drawing of the robot, you can get the CAD for each link and associate to the link the drawing of the CAD. And this is used, for example, to compute collisions. So you can define that with some libraries that you can have a collision if the link, the CAD of the link, the boundary of the represented by the CAD touches the environment, the floor, and you can generate contact forces. So it's very useful. And of course, you have information about the kinematic tree, the joint position, and about the joint positions limits and the velocity limits. Whatever we said, the kinematic limits, there are also velocity limits that you cannot achieve more than a certain speed, usually with an electrical motor. And you can also add sensor models, for example, cameras, sliders, that, I don't know, I want to locate the camera in front of my end effector. I include a URDF model, and you, in essence, import the model of the camera with inside the model, and you can simulate that. The software that are mostly used in robotics, there are many. Some example of them are related to the middleware that, for example, is a software that is designed to manage multiple technologies and provides a common programming abstraction across different parts of the system. Let's say you want to make your controller communicate with your sensor, with your planner, and with and you want to do this in an abstract level. So the most famous way, it's ROS that we will use in the lab, which is called stands for Robot Operating System, and is mostly used in robotics, and is like a data messaging communication technique that you, for example, write your controller in a node that communicates with messages with the sensors, provides messages, and sends messages to the actuators. The problem of ROS is that it's not real time. So you have the real-time version of ROS, which is called ROS control, that solves this problem. YARP is another middleware that was implemented at IIT for the iCab robot. It's a child robot. I don't know if you saw it. It's a humanoid. And then there is Oracos that is real-time compliant, that is more focused on control. As simulators, as I said, they are software designed to recreate the physical behavior of the robot, so to integrate its dynamics and see how it interacts with the environment. And the most famous one is Gazebo, that you will use in your labs, Python labs, and is tightly interacting with ROS. And we have PyBallet that is mainly used from the machine learning community. It's based on the Ballet physics engine to integrate the dynamics. And then there is new one that is developed by NVIDIA that will become soon very, very famous. That is based on, I think it's based on parallel computation with GPUs, because GPUs are the NVIDIA boards that can be used also to parallelize the computation and speed up this way the simulations. Then you, to create the model, you don't do by hand. I will teach you how to do by hand, but it's not really feasible for more than 2 or 3 degrees of freedom. Whenever you have 12 or 55 degrees of freedom, as the case of ICAM, for example, the humanoid with many degrees of freedom, the head, the torso, the arms, then you usually exploit some off-the-shelf libraries that straightforwardly provides you the kinematic model and dynamic model, starting from the URDF, for example. And one of these is called RBDL, that was mainly used in the past. Rockcogen is not based on URDF, unfortunately, but it's using code generation. So you need to provide a model of the robot, and it will provide the kinematic and dynamic library with automatic differentiations. So it will provide also derivatives of the quantities, derivatives of the mass, derivatives of the positions of the Jacobians, and it's very useful if you do optimization. And Pinocchio is becoming very, very famous, and you will have this in your lab. It's based on this library, and it will provide not only kinematic and dynamics, but also the derivatives with the symbolic differentiation, not auto differentiation, and is based on the URDF. So it's the last, the most mostly used right now. And this part is finished. I would go. Do you have any question on this part? Okay, there's a question from the audience. Online guys. I didn't get if the practical side of the course will cover the simulation aspect you showed before, like the simulation of the robot who climbs stairs. No, we will mainly talk about manipulators. So in 6 credits, also teaching about floating-based robots is not possible. So maybe next year, I don't know. You can ask to your coordinator to introduce a course about that. But yeah, we will focus only on fixed-based manipulators. Climbing stairs is for legged robots, and then we go in another topic, which is floating-based robots. So legged robots can control their position with contact forces. Any other question? Okay. Let's start quickly just to this part that is on the introduction to measurements. I need to share screen again. Ah, you should be able ready to see. No, okay. Okay. So in this part, we talk about, this is just the first part. Then we will continue next lecture. We talk about what are the non-idealities in the measurement of sensors, which kind of proprioceptive sensors we have in robotics, the kind of exteroceptive sensors, and also some basics on signal processing. So the term sensors, it defines the set of all the possible electromechanical systems that are used to convert physical phenomena to a measurable signal. And typically, all these signals are of 2 kinds, which means voltage or currents. And so these sensors are sensitive the sensor we want to use should be sensitive to the physical quantity that we want to measure. And the basic phenomena that we can use for sensors are, for example, the angular linear position, the acceleration, temperature, the pressure. In case of hydraulics, you can have the flow rate, which is the amount of oil or hydraulic fluid that is passing per second. Stress, deformations in mechanical beams, strain, which is the effort, localized effort on a mechanical element, light intensity, sound, and usually to the sensor that is sensitive to the physical phenomena, there is a transducer that transforms the output of the sensor into an electrical signal that is more convenient to elaborate the information that is contained. I give you an example. The accelerometer, it's made with a piezo component that is compressed or extend according to a very small mass. We will see that, and creates a charge on its at these extremes whenever there is compression extension. So the transducer will just be, for example, the charge amplifier that converts the charge into voltage. For now, we always consider in this course that the transducer and is incorporated in the sensor. So the sensor provides the electrical voltage or current, but mostly voltage. And after the sensor, we have a voltage, I don't know, that is between 0 and 100 millivolts, let's say. And we want to acquire with our electronic boards, National Instrument one or our custom one, a signal between 0 and 10 volts. So we need a component that does the signal conditioning, that contains an amplifier, for example, in this case, to adjust the range of the sensor to the range of the acquisition of the electronic boards. The sensor pay attention could be between 0 and 100 millivolts, the readings, and from minus 100 millivolts and plus 100 millivolts, and the acquisition board could be between 0 and 10 volts. So you need also to shift the sensor range, not just scale it. And this is the measurement chain that is a series of instruments and procedures that are connected in order to acquire the physical quantity, elaborate it, and obtain the reading at the output. And as I said, this is sensor, transducer, and signal conditioning. The sensor modifies states in response to an external stimulus, then generate a physical signal that is transduced and converted into an electrical signal like a voltage and current. And the signal conditioning is doing the amplifying to adapt the range of the sensor to the range of the acquisition board. Filterings also, because the sensor could be noisy, give a noisy output, and also doing the sampling. Sampling is, we will see, is the discretization of the analog signal. And the discretization is the process of sampling an analog signal that is continuously varying in amplitude and in time, and convert it into a digital signal. So the first block is to sample the signal. So read the analog signal in a certain time interval, and then digitalize. And the digitalization, which means changing the analog signal magnitude that is varying continuously, encoding it into a discrete number of possibilities, which means a binary number, for example. And this is done via ADC, which is analog to digital converter. So of the measure variable that you have, for example, on the left, you can see that there are some components. One is the signal you are interested to, that contains the useful information, the information that are useful for the controller. For example, the position of the joint. You want to control the motion of the joint. Then you have another component on top of that, that is something that you don't really want, but you might want to be able to compensate. So this is the disturbance. For example, in a case of an electric motor, you have the cog in torque that is related to the fact that the electric motor has a not infinite number of poles. So there is like a ripple in the torque that the motor transmits due to this finite number of poles. And this ripple you want to compensate because it creates vibrations, for example. And you can use this, check the disturbance to see, for example, where something goes wrong. You can detect, looking at the signal, you can detect if there is something that is getting loose, or it starts to be a screw that is getting loose, and then vibration increase. So you can see that there is a failure about to come, and you can use this signal for diagnostic. While the third component is just noise, and is due, for example, to electromagnetic noise that couples through the wires. Let's say you are reading your torque sensor there, then your acquisition board is here. You have 1 meter cable that goes from your acquisition board to your sensor. And then even though you use twisted cables that are better for noise rejection, you have your cell phone, you have the Wi-Fi that couples and creates all this noise. So whenever you read the reading of the acquisition board, you see the signal of the force sensor plus all this noise. And the longer is the cable, the higher is the noise. So there is a way to call this that is to evaluate the amount of noise with a parameter that is called signal to noise ratio. It is the level of noise, background noise with respect to the signal, the ratio between the signal and the level of background noise. And so as you see, the real sensors have limitations that are due to the fact that the components they are built upon, they are imperfect, and there is noise in the environment, and all these things are difficult to be modeled, but we have a way to define them with some we have a way to define their impact with some parameters that are derived from the field of metrology, which is the discipline that study measurements. And these parameters that are the properties of a measurement system are uncertainty, which is the estimate of our level of not knowledge of the measurement, which is the quantity we want to measure. And usually uncertainty is defined as a, it follows as a suffix, the measure value with a plus minus sign. So, I don't know, 10 centimeter plus minus 0.1 centimeter, it's the level of uncertainty we have of a certain measure of position. 1000 Newton plus minus 10 Newton tells us the uncertainty of our force measure. Then the accuracy tells us how close the measurement is to the ground truth. So let's say your bar, it's long, you have a bar along 1 meter, steel bar, you want to measure, and you measure, your measure, of course, is not telling you exactly 1 meter unless it's perfectly accurate. It will tell you 1 meter plus 1 micron plus 100 micron, depends on the accuracy of the instrument. So the measurement error is how far your measure is from the real value. And you can improve, in general, the accuracy by doing a better calibration of your sensor. And normally the calibration is done whenever the sensor is installed or whenever it's manufactured. And it's related to the sensor itself, not to the measurement system. The repeatability instead is related to the measurement chain and depends on the component of the measurement chain and represent the capability of the sensor of a system to reproduce the same value over consecutive measurement. So if you repeat the same measure in the same condition, if the sensor has a low repeatability, it means that it's provided always different values. And usually you can express repeatability with standard deviation and variance. So that represent the statistical distribution of the measurements. So a big variance means big, low repeatability. Small variance, very, very good repeatability. Then stability, it's like repeatability, but in the long run. So how our measurement system is able to do the same measuring over time. So let's say after a while, your sensor gets warm, especially when we had this problem whenever we created a force sensor, an impact sensor for the foot of the robot. The robot was walking and each impact was, introducing energy in the small strain gauge, which is the force sensor, how we see how we design force sensors. And this was heating up the component, and after a while you see that was a drift in the measure due to the heat. So or the sensor could wear out, could become old, the plastic could get old. So you can have a different measurement with different time. An important point in robotic manipulators is that accuracy and repeatability can be different in different points of the workspace. So if you look at this, on the left, you have the ground truth value in the middle, and your measures that are spread around. So you have low accuracy and low repeatability. Let's say we want to improve, as we said, accuracy, doing a better, repeatability, improving the components. We buy a better amplifier, we buy, we do a noise rejection in our system, and then we improve the repeatability, but we still have low accuracy. So all the measurements are very close, but there is an offset, a measurement error with respect to the real ground truth value. Then we want to improve also accuracy. We do a calibration, and we can compensate this systematic error, and we have high accuracy and high repeatability. And what is this? What represents this? In terms of accuracy and repeatability, high or low? Is it high accuracy? Yes. And high repeatability? No. It's exactly high accuracy and low repeatability. And this one? No, it's low repeatability. It was a trick. It's the same as this one. But okay, low accuracy and low repeatability. Very good. Then if we go, we buy a sensor, the manufacturer provide us with the data sheet of the sensor, which is the instruction that describe the characteristics of the sensor. And in the characteristic of the sensor, the first parameter we look at is the range, which is the range of the measurable inputs and the range of the associated outputs. So this is the input range, the output range, and where this is the real quantity we want to measure. Let's say a force sensor, I want to measure between 0 and 5,000 Newton because my robot weighs 80 kilograms. So with, I think each leg, whenever it's jumping, can reach up to 2,000 Newton. I want to have a little bit of slack, a little bit of safety margin. So I will buy a load cell of 5,000 Newton range, maximum range. And the output quantity is what is the voltage? I don't know, between 0 and 1 volt. And the sensitivity is the ratio between the variation of the sensor output and the corresponding variation of the measurement. So in your opinion, for example, a load cell that creates 1 volt output with a range of 10 Newton is more sensitive or less sensitive that one load cell that creates 1 volt output with 1,000 Newton? No, it's more sensitive, the one that creates 1 volt output for 10 Newton, because it's able to sense a smaller force, provides a bigger output voltage or the same output voltage for a smaller range of force. Because it's a ratio between the output variation and the input variation. So if you have a smaller input variation and the same output variation, sensitivity is higher. And resolution is the smallest increment that the sensor can detect due to the quantization. We'll see afterwards what is the quantization. So for example, an encoder that has 16 bits, you can compute the resolution dividing the 360-degree by 2 to the power of the number of bits, 2 to the power of 16. And this is the smallest amount of the increment in position that the sensor is able to detect. In the middle, the output is always the same. Whenever there is this minimum increment that is represented by the resolution, there is an output, an increase in the digital output. And the last one is the dynamic response, which is the frequency range for the nominal operation of condition of the sensor. For example, think about a microphone as a range of frequency is sensitive to, and also a load cell. You cannot detect. There are some load cells that are more cheap for sensors. When I talk about load cells, they are sensor to measure force. They cannot detect, for example, very fast impact or spikes. Like if you hammer a piece and a piece of metal or link, and you want to see the very fast peak due to the hammering, you can detect it up to a certain frequency, because a hammer is like a flat spectrum input, so it contains all the frequencies, but the load cell will be sensitive only in its dynamic range. The other one will be filtered out. Then we can see what are the type of measurement errors. There are random errors, that, as the name suggests, are completely random. They are unpredictable, cannot be replicated by repeating the same experiments again. So you get always, whenever you get a measurement, and are strictly related to the level of uncertainty. So the uncertainty depends on the random errors that are added to the measurement. They can be reduced, the random errors, increasing the number of measurements and doing an average, for example. Or using a filter. Systematic errors, instead, are the errors that are consistent across different measurements. If you repeat the experiment, then you will have the same error. You will get the same error. And these elements can be compensated or corrected with proper compensation. In general, the random errors are modeled with white. They are called white noise, and they have a constant power spectral density at all frequency, or they're modeled as a Gaussian distribution, which means in this case, they are called additive white Gaussian noise. So, and in this case, you have a normal distribution with zero mean and some variance. While an example of systematic error is the offset or bias, and it's the value of the output for zero input. So let's say we want to measure force. We don't apply any force, and we see a 0.1 volt reading. So this is an offset, and whenever you want to read the force, we need to subtract in our software this offset such that will correspond the output of 0.1 volt will correspond to zero force. So we can compensate this. Then other example of systematic errors are the linearity error, which is the maximum deviation of the output from a straight line that define the real characteristic. So in general, all the sensors are designed and built to be linear because we are not masochistic people. So we want to work with linear sensors, but nothing is perfect, nothing is ideal. So it happens that the sensor, the manufacturer tells you, you are linear up to a certain range, and then you become nonlinear. So in general, the nonlinearity is defined as a percentage of the output range wherever the sensor is linear. Out of that, you're not ensured of being linear. So you will try to design your system. So select your load cell. If my load cell that we selected for 5,000 Newton range is linear only up to 3,000, my maximum force I'm expecting is 2,000, I'm fine. If I get 4,000 force, I will know that my reading will be wrong out of the linearity range. Then the scaling factor is whatever it's just a gain. So let's say I still have my force sensor, and usually one load cell, one force sensor is providing between 0 and 1 volt, and the other one between 0 and 2. So I need to estimate these gains with the proper calibration, adding weights, and see, okay, for 10 kilograms, I have 0.5 volts, 20 kilograms, I have 1 volt. And then do this calibration for each force sensor, and then I will see the gain of each load cell to apply to the voltage that relates the force I want to measure with the voltage. And the dead zone, it's something very tricky. You can have this in hydraulic valves. Let's say you have a valve that has a spool inside that opens the channel to the chamber of the cylinder. We will see this in the hydraulics. And this valve has some overlap. So in the middle position, there is no flow. Then it needs to move a while and then opens another one of the two channels. Gradually will start to open. But there is a middle range in which there is no output. So whenever there is zero output for a certain input, you have a dead band or dead zone. You can have this also in drivers. If you have an electrical motor, you want to drive a voltage, and you have a minimum voltage that you need to apply to have a current. And this is normally related to the voltage drop on the diode. So you have a dead band also in that case. You can compensate that inverting the band, but we will see this. And then the last one is the hysteresis error, which represents, for example, you have hysteresis when you have elastic materials that exert a certain force if you compress, and another one if you release. So a different behavior in the up range and in the down scale. And also in case of it's like related to a lag, delay between input and output. And normally the hysteresis disappears whenever you are doing very slow motions. But if you do very fast, if you have an elastic element, you have another example, it's a magnetic field in a ferromagnetic material that you magnetize and demagnetize, and you have this hysteresis, magnetic hysteresis, and it's strongly nonlinear. We don't like it. Hopefully, we don't. If you have it, you really have problems. And yeah, I would say this was the last slide. If you have any questions. Okay. Yes.
How do we distinguish a disturbance from a noise? Because we want, as you said, we want maybe to compensate the disturbance, but the noise we should filter. So
very good point. Usually the noise is very high frequency. So normally we distinguish by frequency. If we have electromagnetic noise, we see there's a very high frequency variation that we can filter with a low pass filter that cut whatever is beyond a certain frequency. While the cogging for torques of this disturbance, we can distinguish because we know the velocity of the robot, the motor, for example. So we know, according to the number of poles, that this cogging torque will have a certain frequency. And we can with a notch passband filter, for example, that a notch filter that extracts only that frequency, we can evaluate how much is that and compensate. At least this is what we did so far. But in general, at the frequency level, you estimate. Okay, so if we don't have any question, we continue tomorrow with the other proprioceptive sensor and heteroceptive sensor. And I will put the slides online and hopefully also the recording of the lecture, and try to solve this organizational problem. If you have any issue, just write an email. Okay.